Hello, my name is Riley Pointer, and this is my lab report on Physics Lab 2, Gravity. The purpose of this lab was to observe and analyze the motion of an object that is dropped from rest and falls somewhat slowly straight down. The physics equations at play during this lab were the drag equation, which states that the drag force vector is equivalent to the inverse of the drag coefficient multiplied by the square of the object's speed multiplied by the unit vector, which this equation was used because drag opposes motion to a fluid, such as air. The other equation at play was the gravity equation, which states that the gravity force vector is equivalent to the inverse of the universal gravitational constant multiplied the mass of the larger body multiplied the mass of the smaller body divided by the square of the radial distance between the two objects multiplied by the position unit vector. This equation was used because all objects experience gravity, which is especially noticeable during a free fall scenario. For this experiment, a loosely crumpled sheet of 5-star reinforced graphing paper was dropped from approximately 2 meters. This experiment demonstrated Newton's second law, which states that an object at rest/in motion stays at rest/in motion unless acted upon by an unbalanced external force. Here we have a video tracking the graphing made using the tracker program. Though it's a bit difficult to see, those tiny orange dots on the graph indicate the positions at various timestamps. Those will be better demonstrated at a later slide. This graph is what depicts the plot of my actual observations, that being the recordings shown earlier, as well as the models created using the GlowScript code. The blue line indicates the actual plot shown using the video recording in the tracker program. This This orangish red line right here indicates the plot created using GlowScript, modeling gravity and drag simultaneously. And lined almost perfectly with the gravity drag one is the gravity only one in green. As you can see, the gravity only and gravity and drag equations both are relatively equal. However, the height of the one with drag was started slightly decreasing, indicating that the drag force was having a noticeable impact on the speed at which it fell. During this lab, there were several potential sources of error, one of those being that the object wasn't dropped straight down. This error could have caused the calculations for the tracker program to be inaccurate, as it would have been unable to accurately depict a total without outside interference motion. Another source of error is that the ball could have been made too compact. This would reduce the surface area and therefore decrease drag. And of course, the final one is improper uses of the VPython code editor would have created an accurate graph as seen in the previous slide. So what does it mean? Or more specifically, what does terminal velocity mean? Terminal velocity is essentially the maximum speed at which an object falls once the force of drag is equivalent to the force of gravity. Of the 3 graphs created, none of them actually depicted terminal velocity, because the time the object fell was not long enough. And achieving terminal velocity means that the net force is 0, assuming a straight drop, as that means that the gravity force and the drag force are equal. So, what if? What if the object was thrown downward instead of just dropped from rest? So terminal velocity exists independent of initial speed, as it is as any given mass or object will have a specific terminal velocity regardless of what measure it takes to reach it. It's independent of speed. The only difference is that it might reach terminal velocity faster than if it was just dropped from rest. In conclusion, this experiment demonstrated gravity, drag, and momentum. The observed data did not align with either predicted models, and those sources of error likely impacted said predicted models.